Coming here, the customs officer asked me why I was in Canada, and if colleagues back home asked me this, the taxi driver, and I liked saying I was going to a computational criminology conference and then waiting for their reaction, which usually took several seconds for them to process that and then go, wait, what? What I think of, as computational criminology, at least, what I'm trying to do is basically use computers to help, prevent crime, which it sounds like science fiction, and I don't know if you've seen this commercial. IBM has a nice commercial you should YouTube that basically goes where, the robber is going about his daily routine, going to a convenience store to commit a robbery, and the police officer is, nonchalantly kind of going about his routine, but he knows that what the criminal is going to do before the criminal does, and so he shows up and has enough time to get his coffee, and he's waiting for the criminal to arrive. And this has been airing in the U.S. I don't know if it's been airing here, but yeah, so that's IBM, and it sounds like science fiction, but actually this has already been done. So here's a news article from Santa Cruz where they're using a predictive policing algorithm. A computer told the officers where to go. They went to that location, and sure enough, they caught two people trying to break into cars. So this is possible, and I think this is what we can try to accomplish at a workshop like this. So I want to talk about how we're approaching this problem. So first, and some of this will be redundant with Andrea's talk, but I'll try to give a new spin on these things. So I want to briefly touch upon kind of the behavioral and geographic reasons why we're using the approach that we are, and how we understand crime patterns. And then I want to talk more in depth about self-exciting point processes. And maybe you can come away from the talk with actually, being able to implement your own predictive policing algorithm using point processes. So I'll go into a little more detail on them. And then also talk about how we're using them to predict crime, on a daily basis. And I also want to place them in kind of the more larger context of crime hotspot maps, which are also useful for predicting crime. And then I'll conclude with with a discussion of what we're doing in Los Angeles with predictive policing and how it ties in with traditional hotspot policing. So I like to think about crime patterns in the following way, and I like an earthquake analogy. So earthquakes kind of have two parts to them that seismologists have known for a while. One is there's kind of a fixed environmental heterogeneity in earthquake data, right? So in California, you're just more likely to have earthquakes than in the Midwest because you're along fault lines. So there's an intrinsic risk level that doesn't change over time that says one area is more likely to have earthquakes than another. On the other hand, you also have a dynamic component to earthquake risk, in that when an earthquake occurs, not all the stress is released, but it's transferred to neighboring regions. So you get aftershocks that occur. So when an earthquake occurs, the increase of more earthquakes actually go up. Okay, so this is how I like to think about crime, and I think these two components are also present in crime. So this is a figure that Andrea showed, but I want to say a little bit more about it. So one thing that causes crime to be unevenly distributed in spaces is demographic, social, economic reasons why one neighborhood might have more crime than another. So that's one way you get fixed environmental heterogeneity, or at least it doesn't move much over maybe the scale of several years. I mean, eventually populations shift, but on short time scales, you can assume it's fixed. Even more fundamental than that, as Andrea pointed out, is that there's just some places crime can occur. If you're talking about residential burglary here, this is a block. If you go 2 blocks away, you're in some other region of space where residential burglary can occur. So there's really, on the order of 100 meters or so, crime has a certain type of risk level, and then it abruptly changes. So all those factors play into environmental heterogeneity. Okay, but there's also a dynamic component to crime, as Martin and Andrea pointed out. Just like in earthquakes, if you have a crime that occurs, it increases the likelihood of more crimes. And if you don't believe me, you just ask a burglar, which Wright and Decker did, where they interviewed a bunch of people that had been caught, and they'll tell you, I go back to the same place because I have information on that place. I may actually live in the same neighborhood as the person where I commit a burglary. I know their schedule. Maybe I go back a week later, the same day of the week, because that's a good opportunity when they're at work or not home. An example closer to home for me, and this is just not at the exact same location, but this increased risk diffuses in space. So this is my house here. Last summer we had a burglary next door, and then a couple weeks later my neighbor's car was broken into, and then my bike was stolen from my backyard a week later, and then there was another car break-in, and finally they were satisfied when they had stolen a hammock. And that was the end of this little aftershock sequence. So I've seen firsthand how this type of thing works, and maybe it wasn't the same person that committed all of these, but it could have been, and it could have actually been one of my neighbors. Statistically, criminals only travel 50 meters or so to commit their crimes. Okay, so how do seismologists model this sort of thing? So they've been doing this since at least the 1970s, is using self-exciting point processes. And I like point processes because they kind of work in the currency that crime, really exists in that it's events. It's a points in space-time, which is a little bit different than a time series approach. Because in this approach, you can actually simulate crime data. So as Andrea mentioned, I'll go quickly through this. You have a rate of events that's equal to a Poisson rate that's fixed in time, and this is kind of the environmental heterogeneity. You could think of this being the rate in one neighborhood, and each neighborhood has their own point process associated with it. And then when a crime does occur, it increases the risk of more crimes, so you get clusters of events. And then assuming that G integrates to less than 1, these clusters eventually die out and things go back to the baseline rate. Okay, so I want to talk a little bit more in detail about actually how you go about fitting such a process to actual crime data. And it turns out that to be able to estimate the parameters, it's useful to know how to simulate a point process. So I like the approach where you treat it as a branching process. So now I've added space here. And actually, you can allow this rate that measures the fixed environmental heterogeneity to depend on time, like maybe there's seasonal trends. So I've just added that time in there for generality. So the way it works is as follows. So first you simulate a Poisson process mu in space and time. So I'm assuming everybody knows how to simulate a Poisson process, but if you don't, it's in Wikipedia. So you lay down these events in space-time, and you think of time as just another dimension. So you simulate the whole region of space-time at once with that background rate mu. So those are what the seismologists would call a background or spontaneous event. They just kind of happen out of the blue. And now you simulate the process as follows. So now we want to simulate the next generation or the offspring of those background events. So what you do is you place this kernel, this triggering kernel G down you center at each of these locations, and then you just simulate another Poisson process G at each of those locations. And that gives you your first generation of triggered events. And then you do the same thing again. You center G at these locations, and you simulate Poisson processes again, and you get another generation of events. And you keep doing this over and over again until you have no more events in the space-time window that you're looking at. And that's when you stop. And actually, each of these is a realization of G, the triggering kernel. So that should kind of tell you how you might go about estimating this model from actual event data. Okay, so how do you estimate do the estimation. So it would be nice if you actually knew this branching structure. Because if you did, then it's just very simple density estimation, like Andrea was talking about, where you could use your favorite density estimation technique. You would use these inner point distances to estimate G, and you'd use these background events to estimate mu. Of course, unfortunately, you don't know the branching structure, so that's what makes the problem more difficult. So it turns out you want to estimate the branching structure of this process along with mu and G. And you do that via expectation minimization. Okay, so here's what the complete data log likelihood function looks like. And this is if you knew the branching structure. So UII is 1 or 0, 1 if I is a background event. UIJ is 1 or 0. It's 1 if J triggered event I in the branching structure. And so you can see here it's nice that if you knew the branching structure, this is completely decoupled when you take derivatives of the log likelihood. So you can estimate mu and G independently, and it's really just a density estimation problem. And this was not really recognized until 2008. And it turns out that actually the seismologists were able to kind of guess this without actually knowing they were doing maximum likelihood estimation. So the first appearance of this was actually in the Science. It wasn't in a math journal. So they guessed this form because it turns out that the expectation step is quite intuitive. If you want to know the probability that an event is a background event, it's really just the ratio of the rate, the background rate at that location in space-time divided by the overall intensity of crime at that space-time location. And similarly, the probability that event J triggered event in the future I is just the ratio of the portion of the intensity given by the triggering kernel over the overall intensity. So that's the expectation step to determine the probabilistic branching structure, and then you go back and forth between that and the maximization step. And this is where you use your favorite density estimation technique. So here I've kind of written out what you would do if you wanted to use kernel density estimation, like the Gaussian estimation Andrea talked about. And it's exactly the same, except you have these probability weights attached to each event. So every event is not an actual data point, but it has some probability of being a data point. And the same with the triggering kernel here. So you have these probabilities weighting the kernels. And you could use other techniques as well. A lot of times in seismology, you actually assume some parametric form for G, like a power law distribution in space and time. Okay, just a few more remarks on the expectation maximization algorithm. I want to point out, and this is why I like this algorithm so much, is it's very robust, and it's not sensitive to initial conditions, meaning, of course, it's maximum likelihood, so it's going to converge to a local min. You can't guarantee a global minimum of the negative log likelihood. But basically, any initial guess you give the algorithm, it converges to something reasonable. And in fact, if you have a good separation in your clusters, so meaning that if you kind of looked at the data, you could kind of see the different clusters, it actually performs as well as Newton's method. So it'll converge in about 10 iterations and give quite highly accurate estimates to the parameters. That's because it's essentially a projected gradient descent algorithm. So the condition number of that projection matrix is very good if you have separation between your clusters. Now, it's well known for EM and mixture models that if you don't have separation, then two things happen. One, the EM algorithm converges much more slowly. And then two, you have higher variance in your parameter estimates if the mixtures are not well separated. So that is true here as well. But even in that case, I think for prediction, you still get reasonable results as long as you let it, you take maybe a few thousand iterations to let it converge. Okay, so what do you see if you actually fit these to data? So here's an example of fitting a non-parametric version of this to burglary data in the San Fernando Valley in Los Angeles. And so on the left, you see the estimation of the triggering kernel in time. And what you see here is you have a spike at very short times. And when my guess is that you have this is burglary, so maybe you have a few burglaries right in a row in a few hours in the same neighborhood. So it picks up that kind of trend. And then it dives down, and then at about 7 to 10 days, you have another spike. And again, going back to the interview with the burglar, there's sometimes a particular day of the week maybe when they want to go back. So you can pick that up from the data as well. Now, actually, the repeat victimization risk lasts for several months. So it's not, it doesn't decay back down right away. Another way you can kind of look at this is actually sample from the branching structure. So on the right, in space, I've just centered all the parent events at the origin and then plotted their first generation offspring relative to that initial parent event. And you can actually pick up the block structure in the San Fernando Valley. So, near repeat events in the San Fernando Valley seem to happen within a block or two of the parent event. Okay, so let's see here. How am I doing on time? So next I want to talk about how you might go about using a model like this for the purpose of predictive policing. So let's say I'm a crime analyst, and in this example I'm a crime analyst in Chicago, and I have all the data at my disposal, from the past up till today. And I'm trying to figure out how to allocate my patrol resources. So one way you can kind of think to do this, and this makes sense for several reasons. You want to chop up the city into different regions and then assess risk in each of those regions. So in this case, I've broken it up into 150 meter by 150 meter boxes. Why that scale? Well, it's about the scale that crime happens on. If you take it too large, you're going to encompass parks and residences all in the same box. So you don't want it too large. You don't want it too small because then it's hard to police. Okay, and then so I fit my point process up to the data to today, and I take the boxes that have the highest intensity, and I flag those for patrol. So here I've flagged the top 3% of Chicago using robbery data from 2009 to 2011, and this is what I get. I get these hotspots, if you will, that I should direct my patrol resources. There's about 800 here, and it turns out that there's around 1,000 marked squad cars in the Chicago PD. So technically, they could send a squad car to each of these boxes and have some left over. And the idea would be, even though you're only patrolling 3% of the city, you could maybe deter 50, 60% of robberies by doing that. So you take limited resources and maybe you can prevent a large percentage of crime. One final thing I'll point out is that all this data is open source in Chicago. They have a very nice searchable, filterable, exportable database of crime data online, going back 10 years. So this is a good source of crime data if you're interested. Okay. Now, I want to place these point processes in kind of the context of what people have been doing for quite a while. So for many decades, people have been doing crime mapping. So putting points on a map, and police departments do this to allocate their patrol resources. And it's actually pretty effective, just plotting out crime and going to those areas. Now, one kind of step that's more sophisticated than that is using a hotspot map. Why is a hotspot map better than just putting pins on a map? Well, you're really reducing the variance of the map that you're looking at, because you don't want to just chase random fluctuations. You want to smooth things out so you have a better idea of what the underlying intensity of crime is. So that's what crime hotspot maps do, and these have been proposed and used for predictive modeling. So one approach is to take a time window, so maybe the past several weeks or several months of crime data, and put a kernel down at each of those events in space. So forgetting about time. What is that what are you actually doing mathematically when you do that? Well, you're really assuming that the underlying crime